In the next lesson, we're going to measure the wavelengths of light that an atom emits when you pump a lot of energy into the atom. Specifically, we're going to take hydrogen and pump a lot of energy into it, and that's going to make it glow. It's going to spit out some light. And what we want to do is figure out what the photon energy for that light is. One of the wavelengths that it puts out is 410 nanometers. And what I want to do is figure out what's the photon energy for that measured wavelength of light that I get. Alright, now how would I do that? I know a connection between photon energies and frequencies. Here's frequency. The connection is that the photon energy is equal to Planck's constant times the frequency. So if I can get the frequency, I can get the photon energy. I can use this as a link between these. Now, it's not a conversion factor, but this is a roadmap for doing the problem. Now, here, what do I have? This is a wavelength. So if I have a wavelength, I can always connect that using the wavelength to frequency relationship that we talked about earlier in this lesson. These two are pretty important for you to know and understand. And what we're basically doing here is taking some calculations that we've already done here and putting them onto this one. We're stringing them together in order. So what do I got? I got 410 nanometers. Step one is going to be to go from wavelength to frequency. So if I take this equation and I solve it for the frequency, I can do that by dividing both sides of the equation by wavelength. So what I'm going to get is frequency is going to be equal to the speed of light divided by wavelength. Let's put our speed of light in there. 2.9979 times 10 to the 8 meters per second. So I have to have that handy to do the problem, and I've got that in the problem below this. Divided by the wavelength. Now, that's not going to come out right because I don't have the same units for length here, meters here and nanometers here, so I have to turn them into common units. The easiest way to do that is recognize the nano there means times 10 to the minus 9. And just write it in like that. And now we've done this kind of thing before. Let's just punch it in. It's going to be 2.9979 times 10 to the 8th divided by 410 times 10 to the minus 9. And that's going to be 7.3119522 times 10 to the 14. It's an intermediate result, so I'm not going to round it off. And let me see, I'm going to get 1 over seconds for my units, which is a good frequency unit, which tells me everything looks good. So now the next thing I'm going to do, now that I have the frequency, I'm here, I want to go to the photon energy. The photon energy is going to be equal to Planck's constant times the frequency, which is equal to Planck's constant. I have to have it handy, and I've got it listed for you below, times 10 to the minus 34 joule seconds times the frequency that I just figured out. Now, take a look at what happens to the units when I multiply these things together. Joules times seconds times 1 over seconds will give me joules, which is the correct unit for the photon energy. And all I got to do is take that frequency I just figured out and multiply it by Planck's constant. 6.626 times 10 to the minus 34, and I get it. The photon energy is going to be 4.8448 other stuff times 10 to the minus 19 joules. All right, how about significant figures? Pretty easy, because let's say I knew this starting wavelength to 3 figures. I'm only going to know this to 3 figures. That looks like only 2 figures, so if I didn't know any better, I'd say round this off to 2 figures. Say 4.8 times 10 to the minus 19 joules. I couldn't fault you for doing that. But if the person who measured this told me I knew this to the nearest nanometer, then I'd have 3 figures there. So I'd cut it there. If I had 3 figures in my wavelength, I'd cut it there if I had 2 figures. We're going to do a lot of problems like this in the next worksheet. In fact, if you can do this particular calculation, you can do everything in the next worksheet pretty well.